like to compare different types of background, then I would say that the most complicated two types are muon background and neutrino background. So neutrino background can be reduced only because of low pressure within the decay volume, but there are still some amount of events that you cannot reduce because of interaction of neutrino near the walls and in the end of the shield. And this type of background can be reduced by reconstruction of vertex and applying cuts. So I would say that it a little bit simpler than muon one, and muon background particles from muon background can come from the interaction with the walls of the hole where the ship is placed with the mountain, let's say. And if muon will be declined by this wall and return inside the ship, it is very hard to simulate such processes, but we still believe that it can be measured because of this big scintillator around the decay vessel.
And you mentioned that you have cuts, but how do these cuts and selection criteria impact the signal? So what is the efficiency that you lose typically with these cuts that you mentioned?
There is the usual cuts for reconstruction of the events is to have two well reconstructed charged tracks that we can reconstruct up to decay point, and this decay point should be within some fixed volume that we believe that the background event shouldn't be decay within this volume, shouldn't interact within this volume. So this of course reduce efficiency of the events, because not every event will produce these charged tracks inside that will go inside the detector, and in our estimate is the following. First of all, there is a geometric acceptance, which means that not every HNL, not every new particle candidate will go within the decay volume, and this is roughly 1/3, so 0.3. It of course depends on the mass of the candidate and interaction physics of production, but in average it's around 1/3. And there is additional acceptance coming from the fact that decay products of the new particle should produce these two tracks. It's also around 1/3. So if you multiply this number, you'll get 1/10.
Okay, can I ask another question?
If it is a brief question, yes.
Yes, I make it very short. So if you want to go to the bottom of the seesaw in the HNL, what would you rather do? Enlarge the cavern, increase the number of protons, or what technologically, do you know what is the...
It's very nice question. So if you want to go to lower interactions, there are, of course, the main strategies is either to increase intensity or to increase decay volume. In the initial project of ship, there was 2 decay vessels, and these will roughly increase our number of events by factor of 2, and this will lower the boundary for the interaction squared by the factor square root of 2, because we are so-called U to the power 4 experiment, which means that this small interaction comes in the number of events to the power 4. So I would say that both strategies are equally good. So if we have let's say, financial possibilities to produce longer decay vessel, the sensitivity will be proportional to the length of this vessel. If we have, again, financial and financial possibilities to increase intensity and to make our process longer, again, number of detected events will be proportional to the time of the work of ship experiment. So it would be nice to use both of these strategies.
Okay, thank you very much. Then the examination shall be continued by Professor Rogajski from the University of Copenhagen, whom I also welcome here at Leiden University and at this table. The floor is yours.
Thank you. Mr. Candidate, I would like to ask you several questions regarding the motivations for the models that you study in your very nicely made thesis. First question concerns neutrino portal. You correctly say that neutrinos of the standard model are massless particles. However, as you understand, they could easily be made massive by just trivially extending the sector with their right-handed counterpart. What motivation did you have to extend this with additional Majorana mass and going into this whole phenomenology of heavy neutral leptons? Why not to be satisfied with the simplest possibility?
How clear the opponents? I thank you for a very nice question. It's also always very nice to go to the basis of and to ask yourself, why do we search for this specific particle and not interested in the simplest model? I would say that first of all, as you mentioned, in the standard model we assume that neutrinos are only left-handed, and we have no possibility because of this to write down the mass of the neutrino, mass term for the neutrino particles. However, if you add also by hands in the standard model right part of the neutrino field, you are able to produce mass of the neutrinos through the usual Yukawa interaction. This of course will give you some observable results, such as where we can look for the observable difference between standard model and this model with additional right-handed neutrino. First of all, in the laboratory experiment, we can look at the decay widths of Z boson, or we can look also at the oscillations of the neutrino. So, because of the existence of right-handed state, there will be possibility to decay in the right-handed state, or because neutrino have mass, the initial left state will have during the free flight will have some mixture of right state. These bounds, I would say, not very tough, but more rigorous boundary comes from cosmology. And if we add 3 additional types of neutrino, so to add right-handed particles to add 3 new types of neutrino, and in the early universe there will be thermal processes during which this right-handed part will thermalize with all other media, and we will observe this by different prediction for Big Bang nucleosynthesis, I would say. So the Big Bang nucleosynthesis is the most striking result that tells us that we cannot just add 3 additional right flavors to standard model. That's why we are adding new types of particle, which is massive right-handed sterile neutrinos. They interact with standard model super weakly, and they don't thermalize during the initial epoch.
Continuing with question about your models, you also consider so-called dark scalars, again super weakly interacting particles. And as Professor Sarah asked you about the bottom for the neutrino portal, I would like to ask you, is there a similar bottom for the scalar portal? When would you decide that you exhausted all the possibility and you don't have to search anymore? Or would you do it indefinitely if you would have infinite time, money and energy?
However, the opponent. Thank you again for a nice question. And I would say that scalar model is a little bit different from the neutrino model, because in the scalar model, the scalar particle itself does not explain such observable phenomena as baryon asymmetry of the universe or neutrino oscillations. That's why we don't have such amount of condition and boundaries on this model. We can assume that this additional scalar is just a portal between standard model and some new physics. And in different theoretical extensions and different models for this new physics, you will get different results for the needed interaction rate of this scalar with standard model to produce reasonable amount of dark matter, for example. So, but in general, if we just search for some scalars that interacts with new sector, new hidden sector, we just don't have any bottom line in the scalar portal.
So which essentially means that you could continue searching for as long as you have such possibility.
Let me answer in the following way. Supersymmetry can be either found or
given up.
Given up. Yes.
So you say that scalar is a similar.
Yeah, the story for scalar, I would say, is similar.
Thank you very much. Do you have time for a short question?
Yes.
Okay, so my last short question would be the following. Your thesis is called Plan B for particle physics. What if Plan A works and tomorrow LHC reports the discovery of new particles? Will all your research be useless from that moment on?
However, opponent. So, I would say the following. Plan A was to find some additional particle at LHC, and if these new particles would be found tomorrow, first of all, it will be super fascinating, and I will be very happy because of this. But nevertheless, even if in all this model proposed for LHC, for example, for supersymmetry, there are always a possibility that new light feebly interacting particle exists in the spectrum. So I would say that even if we found some new particles at LHC tomorrow, we still need to search for feebly interacting particle to complete our picture and to test the properties of the new theory.
Okay. Thank you very much.
Thank you very much. Then the examination shall be continued by Professor Dekowski from the University of Amsterdam, whom I also welcome here at this table and at this occasion. Please, the floor is yours.
Thank you, Mr. Candidate. Thanks for writing a very concise thesis. It was nice to read. I have a few questions on the detection capability that you've investigated, and I'd like to start with the Methuselah tracker that you describe on page 66. And I would like to know a little bit more details of what is actually required of this tracker in order to be able to do this measure.
Okay. Cognitive opponents. Thank you very much for your question. I studied in my thesis few experiments, namely sheep and Methuselah, and for Methuselah experiment there is still not well experimentally developed proposal. There is the proposal for the Methuselah experiment is I think will come in probably half a year, and there is experimental collaboration of Methuselah experiment who is investigated which concrete sensitivity should have this tracker of Methuselah.
I'm actually curious what you would recommend for this. Since I mean, you're proposing quite an ambitious tracker, right? 200 by 200 meters, 20 meters high.
Okay, let me answer in the following way. There is a nice paper from the more theoretical side called Methuselah Physics Case, where in the first part of this paper, people from Methuselah collaboration discuss that there is well-established technology for the tracker, and to be honest, I don't remember the name of this technology because I'm more from theoretical side than experimental, and they say that using this specific technology, the tracker with reasonable sensitivity can be made with financial scales comparable to the sheep experiment.
Right. What I'm interested in is what is the key property that you need? I mean, I see in...
So the idea was the following. So you use some layer of scintillator material, and after this you put a layer of some absorbing material like lead or tungsten or something like this, and again layer of scintillator, layer of some absorber material. This gives you an opportunity to not only restore the track and to see the direction of the track, but also using the knowledge of the width of this absorbing material, measure energy and even type of particle, because different particles will behave differently in this absorbing material.
I see. Okay, maybe we should move on to another question I had on page 80, where you discuss various benchmark models that you've studied for SHIP and Methuselah, I guess. Can you say a little bit why you chose the specific benchmarks on page 80, BC 6 through 8, and
Very opponents. The answer to this question is pretty simple. These particular three models were chosen because for these particular three models we think that successful baryogenesis is possible. So the idea of this HNL model, which is called new MSM, is not only to explain neutrino oscillations, but also explain baryon asymmetry of the universe and give a dark matter candidate. So
but when I look at it, it seems like to be very different ratios, right? The whole parameter space.
So the answer is the following. Within the parameter space of this model, there are many points that are able to produce baryon asymmetry. These particular models are maximized within this space of successful models for baryogenesis. They are maximized by one of the mixins. First one is maximized by electron mixin, second by muon, and third by tau. So, and I want to comment additionally that these particular values were a little bit So currently these particular values are a little bit outdated because very recently came up new study about generation of baryon symmetry at within the new MSM model, and we need to continue research and a little bit upgrade our results. But as a result of my work and work of the collaboration, we are able right now to produce sensitivity to any pattern of mixing very fast.
Okay, so since we're on this page, perhaps the sensitivity curves for these three models show a very similar pattern, right,
Yes.
if I look at it. Can you say a little bit more what determines that pattern?
Of course, it's so completely opponents. Thank you very much again for very nice question. It's very close to me, and I with big. So I would like to answer this in the following way. So the curves are, if you compare these curves at figure 5.9 and previous 5.8 in the previous page, you will see that all of them are quite similar, and the main features are the following: between 1 and up to 2 GeV, the main production mechanism of new particles is decay of d mesons, and we have at ship a great amount of these d mesons. That's why the sensitivity in this region up to 2 GeV is so high. Then, because of kinematical constraint, the production from d mesons is not possible anymore, and next comes the production from the b mesons, more heavy mesons with big work. So because of smaller amount of these b mesons, the lower bound of the sensitivity curve is a little bit higher. There are additional let's say feature around 3 GeV, and this feature coming from the different decay channels of B meson. Between 2 and 3, the main contribution comes from 3 body decay channels of B meson, and above 3 GeV, the main production channel is 2 body decay channel. And the last that I wanted to comment is the upper bound. You see, every of this figure have additionally upper bound of the sensitivity, and this upper bound just coming from the fact that if you have too high interaction, too high value of the coupling constant of new model, new particle would decay within the wall of absorbing material that we put before the decay vessel.
Okay, thank you very much for a very clear description.
Okay, thank you very much. Then the examination shall be continued by Dr. Samtleben.
Mr. Candidate, I read with pleasure your thesis. It's a very detailed document describing all sorts of decay possibilities, detection possibilities, discovery possibilities for us. So let me briefly start with a technical question on figure 3.3, which you showed there's a decay width of the heavy nickel-lectins. If I understand it correctly, this should correspond to a fraction that is maximally 1, but maybe I misread this or misinterpret this figure, so I would be happy if you can explain a bit on this value.
Declare the opponent. Thank you very much for your question. So about this figure 3.3, it is shown in such a way that it seems like the branching ratio for some specific channel, namely kaon decay to the electron and sterile neutrino, could be greater than 1, which of course is not possible, because branching ratio is defined as just decay width by this channel divided by total decay width. But what we see here is the following. In the denominator of this expression actually stands standard model decay width of this kaon. That is why if you add to the standard model some new particle with very high interaction rate, the decay width by this particular channel divided by decay width of the KN in the standard model can exceed 1. So of course, this doesn't mean that if you search for sterile neutrino, you expect such great decay widths. This picture is shown specifically for the mixing angle equal to 1. In reality, this value, of course, is excluded experimentally. And currently, we search for mixing angle around 10 to the minus 8, 10 to the minus 9. So if you would like to understand the real branching ratio of the HNO candidate, you need to multiply the values at this figure by 10 to the power 16 around.
Okay, thanks a lot for this explanation. So I have some other question also on your figure 5.6, which shows the sensitivity, where you map out and compare the chip one time with the charm contribution and one time without to Methuselah. And for Methuselah, you explicitly say in the legend, so this is an ideal detector. We assume that everything has been detected. So is that a fair comparison with respect to what you investigate for SHIP? Because for SHIP, you always have the constraint of real detection according to your simulations.
Thank you for your question. The answer is the following. For SHIP experiment, during the time where my thesis was written, we already had full-scale simulations of all the possible backgrounds, were developed plan for the experiment itself, and we can do realistic estimates. So we take into account geometrical acceptance, we take into account the acceptance of decay products. But for Methuselah experiment, there was no well-developed simulation suite, and we did preliminary estimates using the maximal possible income. So we of course, in reality, I don't expect that that efficiency of Methuselah experiment will be equal to 1. Of course, it should be smaller, but still I expect that it will be too small. Methuselah experiment has nice ideas how to reduce the background, and the cuts using for this purpose are not very strict. So
can you maybe elaborate on the background in suppression for Methuselah? In which way is it different, or more challenging, or more restricting, or less restricting than what you do for chip? Because it's sitting on the top of the surface.
On the Earth, yes. Okay, so for Methuselah experiment, the main types of background are the same as for SHIP. There are high energy neutrinos coming from interaction point from experiment under the Earth. It should be CMS or Atlas. There is cosmic rays from above mainly, and there are high energy muons. High energy muons should be almost all shielded by the 100 meters of material between experiment under the ground and the surface. High energy neutrino can be constrained by the criterion that all the high energy neutrinos should produce a proton, and people from Methuselah expect that they will be able to detect this proton from interaction. Then about cosmic rays, the idea is the following. Cosmic rays are coming from random directions, and if you measure direction of tracks, you are able just to reduce neutrino background from the geometrical point of view. So I would say that the cuts and the strategies for Methuselah chip is a little bit similar, because both experiments have some point from where coming new particles, and they both have from this point neutrino background, high energy muon background, and additionally random cosmic ray background from elsewhere.
Okay, yeah, I think it is impressive. You say you expect an efficiency of almost 1 with background-free detections. That sounds quite ideal to an experiment.
If you assume that you have 200 meters by 200 meters of scintillating material, and this scintillator material is in the layers, in 4 or 5 layers, and width in the total width of 5 meters, if there is some decay of high energy particle inside the volume of Methuselah experiment, you almost always will detect the charge products.
Mm-hmm. Okay, I have another question of mine. So I would like to go to figure 5.1 and 5.2. Those are the figures that I find most striking here because they finally show some also experimental data points and experimental error points. If you look at the modeling and if you look at the data points at first order, you say they match quite nice, but this is of course because you have large error bars, then things will match nice. Similar, the measurements of heavy quark production are at the center of mass energy where you're looking not very precise. There's an uncertainty, there has not been an exact mapping, so you have some estimates, and I was glad to see my old thesis experiment cited in the thesis. Here, Herabe has measured some charm cross-sections. How much will these uncertainties affect your final outcome? So how much did you take that into account to see if there's...
Thank you very much for this question.
If I could have a brief answer, please.
Very brief answer is the following. This estimation is for Methuselah experiment, and for Methuselah experiment there is problem of this number of mesons. Number of mesons at low energy is not well defined and not well measured. This will change this could possibly change the number of events by factor of 2 and the sensitivity by factor of square root of 2.
Okay, thank you very much. Then the examination shall be continued by Dr. Silvestri.
Mr. Candidate, I would like to follow up on the Plan A versus Plan B discussion. And so if there was a hypothetical Plan A particle to be detected next week or next month, would Plan B particles be only a possibility, or would you still need them to fully address the beyond standard model problems that you mentioned in your thesis?
The clearly opponent. Thank you very much for your question. The answer is the following. Depends on the physics that we will discover. So, as we know, if we consider some high energy physics, physics at high scales like electroweak scales or higher, supersymmetry or different other types of physics, in many of these physics you can assume mechanism to produce baryon asymmetry, to have dark matter candidate, even to have oscillation of neutrinos. But this doesn't mean that if we find one particle from whole this family, these few particles will already explain all these observable phenomena. And there is probability, of course, that we find, for example, supersymmetry or compositeness of Higgs or other stuff, extra dimension. And we still will not be able with this new physics to explain oscillation of neutrino. Then we need to search for sterile neutrino, for example, as a model that can explain oscillations of neutrino by introducing small amount of new particles.
Thank you. Shall I proceed with another question?
If you have a brief question, yes, please.
Yes, okay. I had a question about the proposition number 2. Can I ask one of the parameters to quickly read it?
So the proposition number
2.
After the discovery of the Higgs boson, for the first time in many decades, we do not have any concrete prediction where to look for new physics. As a result, new types of experiments, such as intensity frontier experiments and/or non-collider experiments and model-independent searches for new physics, become more and more important.
Thank you. I would like to ask you to briefly comment on what this implies in terms of strategies. So how different type of strategies in terms of data analysis and data selection, etc., do we need with respect to Plan A experiments?
Thank you for a question. The answer here is the following. Right now we are in a situation where we are in free sailing, so we don't have any particular direction to go and find the new land. We expected that new land will be found at LHC already, but right now we see no signs, no signatures of new physics. And there are two main ideologically different possibilities. Either you build new collider with higher energy and expect that you find new particles there, but to really believe in this, you need to believe in some additional principle that exists in the nature. For example, principle of supersymmetry, principle of extra dimension. So that will give a scale of new physics close to our scale, because there are very huge amount of energy scale, so huge amount of possibility to put new model between our scale and Planck scale. Or you would like to test possibility for new intensities, for new feebly interacting particles, and in this case you need to produce something like SHIP, Methuselah. So I would say that these two strategies are complementary to each other.
Okay, thank you very much. Then the examination shall be continued by Professor Eliel.
Dank u wel, meneer de rector. Meneer de kandidaat. I will now continue in English. I was intrigued by your figure 6.9 on page 95. And part of my being intrigued is, I was endeared by your handwritten 50 mega electron volt there. That was very helpful. But what I think I missed was the fact that this region in which is written cast and Sumiko actually has very lightly dotted. So you have to look at oblique angle at your thesis to see that that's not white. But you know, your figure caption is rather terse, and so what I don't see is there's all kind of gray and different gray and dots, etc. But what are now the bounds? Because you say there are bounds, but I just see a lot of gray. And so maybe you can explain to me where is the light, so to say? Where should I look?
Thank you very much for your question. Yes, I agree with you that printing of this figure should be in color, and if you take, of course, electronic version of the thesis, it will be easier to find this.
I don't have that
white.
with me.
Yeah, of course. So my answer is the following. So first of all, this figure is about very interesting candidate of new physics, which is called axion-like particle. So this particle is very interesting because introduction of this particle at very different scales can still, for example, explain the dark matter.
Okay.
Because axion particles within this model of axions, the production of axion particles could be non-thermal, and this give rise to the to arbitrary number of produced dark matter, for example, such that we observe in our world. So the possible regions are the following. One of not closed region is between 10 to minus 12 to 0 in the lower scale, so it will be probably helpful if I put some.
Yeah. Okay, there.
So
yeah.
here in the bottom of the figure, because in this region the interaction of axion is too light to somehow deviate the results of the astrophysical processes. For example, here is the SN 1987A is explosion of supernova and some bounce from the explosion of supernova on the axion-like model particles. And another region is in this region on the right, and this region is not closed by current experiments because, again, here is interaction strength is small, but also the mass of the new particle is too high to be produced in stars or in supernova explosions or in some such kind of processes. So this region can be searched only at colliders.
And do you believe it is a good region to search or not? So so you say we have two regions where we can search here.
Yes.
And which one would you prefer?
I would answer this the following way. We should search currently we should search in those regions that we can probe.
Yeah,
And only actually this collider region can be.
Mr. Candidate, the time allotted to the examination of your dissertation and its propositions has passed. The committee withdraws in order to deliberate, and I request that you and your company await our return here in the Senate room.
Все-таки это не овечка.
Почему некоторые графики были в черно-белом?
Потому что печатать цветной не стоит. Я полистал и выбрал те страницы, где уж совсем точно надо цветное. А про это я подумал, что черно-белое сойдет. Например, вот тут цвета разделяются штриховкой, то есть тут более-менее. А вот тут без цвета вообще не поймешь, что где. Да. Поэтому вот про эту конкретную картинку, про аксионы, что мы обсуждали, так она, я когда смотрел в черно-белом варианте на компьютере, то прием все-таки довольно неплохо отличался от белого, я решил, что так себе. И в принципе,
Ну то есть можно, конечно, присмотреться, там точки есть.
конечно, лучше было бы это в цвете. Вот эти 50 метров, пока не отличаться не стоит.
А сколько стоит печать?
Я нашел очень дешевую фирму, и мне печать 50 копий стоила 300 евро. Это считается дешево тут. Некоторые люди там до 1000 евро тратят на печать. Ну, правда, они и печатают больше 100 копий.
У нас еще даже там онлайн, короче, цитировал в слайд, типа, снова скидывал статью, где они, короче, запросили всякие разные тренды.
Вот сейчас они посовещаются.
То есть сейчас они совещаются, потом возвращаются и объявляют, что
Не защитились, да. Слишком много говорил про овец. Сходи-ка попаси овец.
На, поди-ка отличи.
ты не забудь встать, когда мы будем. Суд идет. вот это Эвин Дишок, она получила как раз Галловую премию в этом году. Вот в шапочке, беленький фон.
Что-то вообще.
А, видишь,
В нижнем ряду.
да, женщина в красном с ней рядом.
Это где было? Это сейчас из Дума, по-моему. Да, короче, храм.
Всех женщин вводил УГ по мистерии. А это вот где здесь висят, это просто там выдающиеся профессора, да?
Не знаю. Он Жан Хенрик Уорд, например, сверху. Только это видимо, Уорд.
Ну, тут Уорд, по-моему, это
Ну, вот тут верхний это известный нам, да, вот это какой-то древний Уорд, говорят, 1836 года.
На фул профессора Алексей
Не имеет права.
Нет, когда
сейчас уже фул профессор.
Алексей сейчас зачитывает праздник года.
Я тут вот, видишь, отстреляться не мог.
Не, они молодцы, что положили, потому что...
Максима напрягли почитать немножко. Что? Максима говорю, напрягли почитать
Please take your seats. You may have an answer, if that's okay. Mr. Candidate, we have examined your dissertation and the propositions appended thereto. We have heard your excellent defense, and we have considered the report by the faculty concerning your previous study. On the basis of this, we have decided to admit you to the doctorate, and in view of your outstanding qualities, this distinction. Dr. Bujarski, your promoter, is empowered to confer that dignity upon you in the customary fashion.
Volharden aanvaard ik de taak, mij door de rector magnificus der universiteit opgedragen.
You have to read the text.
English version, I guess it's here.
With kracht dan van de bewoonheid ons bij werd te henken volgens het besluit van de commissie hier tegenwoordig verklaar ik bij deze meneer Bondarenko te bewoorderen tot dokter. Ten bewijze hiervan zij u het diploma door rector, secretaris en promotor ondertekenen en met het grootzegel der universiteit bevestigd te gaan worden gesteld. Having completed the duty assigned to me, I may be the first to address you as doctor and to congratulate you on the awards of the dignity you have obtained in such meritorious way. The honorable distinction is well deserved and highly valued privilege. At the same time, you are called upon never to lose sight of the obligations it imposes on you in the name of science and society. My task is now at the same time is very easy and very difficult, because it's very easy to say a lot of good things about Kirilo. It is difficult not to say too much from pedagogical point of view. So the couple of things I would like to say is that one of the facts that impressed me a lot was when we prepared the defense, we looked at his list of publications, and it was on my screen, and he realized that he has already 11 papers published or in preparation during his PhD. And his reaction was the following. The first question was, did I do all this? And the second question was about another PhD student, and he said, does he have as many papers? Do we need to help him? So this was his attitude, always. Not only doing very well his work, being extremely curious. If you look in his publication list, you can find papers on various subjects, and this is all coming from his enormous curiosity, but he was also always very, very ready to help anybody around him who would require help, and this is amazing. He was also a perfect teaching assistant for all my courses. I cannot imagine how I will teach without him. And he was always graded by the students much better than me. So this, I think, is related to the previous point. And as Nico mentioned during our discussion in another room, this is a unique case where a theorist gives a very significant, makes a very significant contribution to simulations and estimations of signal of experimental collaboration. It's unfortunately not very often these days, because there is too much of separation between theorists and experimentalists, which causes problems on both sides, I believe. The unique importance of what Kirilo did was that he was very, very deeply into all details on all theoretical work and all experimental work, such that he could give really very reliable results. So I think he was probably the best PhD student I ever had, and I hope, I'm sure he will have very successful academic career, because this is apparently what he wants, and this is definitely what he can do.
It is an agreeable duty for me, very learned sir, to congratulate you upon your degree, also on behalf of the university and its Council of Deans. And herewith I declare this ceremony closed.